general is going to take over. Okay, so that's the maximum mode, maximum mode. We have a bus controller 8288. 8288 bus controller is the general. He's going to take some routine work, right? Take over some routine work, right? So that the president can do some other work, important work. Now, how do we know the 8288? How do we know what instruction to generate? We have a 3-bit code, S0 bar, S1 bar, S0 bar. That's the input, right, to the general from the president, which is the microprocessor. And we are going to understand the code and then coordinate with all these signals. For example, memory read control bar, memory write control bar, advanced memory write control bar, I/O read control bar, I/O write control bar, advanced I/O write control bar, interrupt acknowledgement, data transmit receive bar, data enable. See, that's the general 8288 is going to do. It is okay, right? So the way the general is going to coordinate these control signals, as we showed you here, for maximum mode, right? To coordinate the read-write memory or I/O instructions. Now, let's say here, what are the 3-bit code from the president? S2 bar, S1 bar, S0 bar. 000 means interrupt acknowledgement. There's an acknowledgement, I received an interrupt. Now, the corresponding signal, we should set the interrupt acknowledgement bar to be 0. We're going to do this 82, 88 bus control, the general. Again, it is 001, read the I/O port. I want to do this, right? Now, the general is going to set the I/O read control bar to be 0. 010, write I/O port. I want to write I/O port. Then the general is going to set the I/O write control bar 0. Advanced I/O write control bar 0. Right. Now, 011 halt non-operation. 100 instruction fetch. The general is going to set the memory reader control bar 10 because you're going to fetch the instruction from memory. So you're going to read the memory, right? And the 101 read the memory. You're going to read the memory. Set the memory reader control bar. 110 read write to memory. Set the memory write control bar to 0. Advanced memory write control bar to 0. 111 passive operation. Any question?
No.
Get the code. And then generate the control signals for the president. That's what the general is. Who is the general? 82, 88 basket. See? You see that word, we talk about a lot of this the signal. That's the reason we want you to draw the map and mark the full names. Because if we don't know these names, we're going to get lost, right? This control signals. Any question? Any question? So that's good? Now, this one shows the connection, right? 80, 86, 88 about controller. Where's the president? Yeah, 80, 86 microprocessor. And this is the memory I/O interface, right? And where's the general? General. 82, 88 the controller. He's going to take the code. S0 bar, S1 bar, S2 bar from the president and then generate all these control signals in order to coordinate the whole process to get it done. That's the maximum. Okay, right? Get the code, understand it, and then generate the signals to control the whole process. That's the reason. See, each Arduino project group, we want a group leader. You're the general, right? You're the general. So you're going to coordinate your group. Do this, do that, do this, do that, keep moving forward, right? So you're going to generate control signal to collaborate with the whole group. Okay, maximum mode, right? That's the maximum. But the minimum mode, we don't have this general. Your microprocessor has to generate all these control signals to control this I/O and memory devices. Okay, that's the difference. Now, this one shows the bus controller maximum mode. Just now also draw the map, right? That's the minimum mode. Now, for maximum mode, again we have a map. Okay, see we have a lot of maps, right? So this map, we have the microprocessor and the what? Bus controller, H2, H8. So in this way, what signals are there? Again, I leave this for you to draw at home. We don't have the time to evaluate the drawing on the whiteboard, right? But it's a good practice. Maybe in the final exam, we're going to ask you to draw this map, right? And then mark the signals. Okay, what is the president? What is the general? What is the code? Okay, so 0 byte, 1 byte, 2 byte. Right? What are the control signals? Memory reader, memory writer, advanced memory write, reader, and then advanced I/O read write. Right? And these are the A memory I/O bus controller. Right? Which mode is this connected to? Is this set to? Minimum or maximum mode? Minimum or maximum? How do we know? MX bar. What is it can do? 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 Too well. Can do well. Ground. Very good. Ground is 1 or 0? 0. Now it's in which mode? MX bar. Which one is enabled? Maximum mode, right? Right, good job. Right? So that's how we tell. So we look at the MX bar. Whether it is a B or ground is 1 or 0, then we know. Good job. Okay? So in the future, I want you to be able to tell. And I want you to be able to set. Right? Minimum, maximum. Check. Good one. Right? Good one. Now, this is for 8088, probably 86. Very similar. Just we have one high level bar and a few pieces other IO bar and MIO bar, they are opposite. President, general, come on, the code, right, the code, okay, right, and then these are the bus controller signals, the general is going to be code. Okay, any question? Right, so this shows the code and the meaning and the control signal you have to generate. Okay, right? Now let's look at the break it down. Right, this is actually this here, right? Bus controller, log signal, right? Log signal Q, status Q. Q status 00, no operation. 01, first byte. 10 high, and the Q is empty, and the 11 is a subsequent byte. Okay, this is actually for the Q, the status. Now, if the bus status is 2 bytes, 1 byte, 0 bytes, 101, what's the meaning? 101. And what signal should be set? 1 or 0? The general, the president has a code, 101. What's the meaning? 101. What's the meaning? 101 means the president wants to read the memory. Now, what the control signal should be set? Memory reader control bar. 0 or 1 should be set to be the general set to be 0 or 1. How do we know? 0 or 1. If I wanted to read the memory reader control bar, should it be 1 or 0? 1? 1? What value? What value should we set? 1? 1? So we have a bar in the name. What value should we set? 0. Very good, very good. Right. So okay. So that's the reason we have a bar. Right. The meaning is active low, active low. Good job, right? So the way the general is going to set the memory reader control bar to be 0 to get job done. Okay. So is this okay? Look at this table. Right. Look at this table. You have a bar, you don't have a bar. That make a difference. Now this is a voltage signal, right? And this is a clock. Clock. Do we need a clock? We need a clock, right? Otherwise, we don't know what time to start the clock, what time to finish the clock. We need a clock. Clock synchronize all the events and our behavior. Okay, right? We need a clock. Similarly, microprocessor need a clock because every event should trigger this to happen in a certain well-defined sequence. Don't mess up. If you mess up, then it's a nightmare, right? Nightmare. Okay. So this clock, how do we generate it? That's very important because the whole microprocessor count on this clock to regulate its aligns the events, right? So if there's some glitches on the clock, some like delay on the clock, that could cause bigger trouble for the microprocessor. Now, how can we generate this clock? How do we get a clock? We have a clock on the watch, we don't have a clock. It's all program using Apple Watch, right? Okay. But if we have a wall clock, what is that stuff? What is it made of? Quartz, right? Quartz. Okay, very good. Swiss watch. Very proud, right? Swiss watch. Swiss watch is proud. It is actually very famous for its what? Not for its price, for its accuracy, repeatability. Right? After running for 10 years, the error should be less than 0.0001 microsecond. That's a good clock. If you say every day, my clock slow down by 10 minutes. Now, do you want to buy this clock? No, right? Nobody's going to like it. Okay, that's a junk. Right? That's a junk. Okay, so a clock should be very accurate. Now, why do we choose quartz? Why do we choose quartz? Why can't we use stainless steel or some other material, diamond? Why choose quartz? A lot of Swiss watches on the wall, they're made by quartz, right? Why quartz? Why quartz? Because it's beautiful? Because of what? Okay, quartz is a popular material for watch, right? Or clock. Why? Anybody from material science? Yes.
Because quartz makes the power.
Makes the power?
Yeah, it vibrates when you squeeze it tight, it vibrates.
Oh yeah, make the power. And the energy or energy to the power. Oh, okay. So that's one answer. Okay. But the quartz material, I think the reason we choose quartz is because of what? It's accuracy. Accuracy. If we say that we make some like material science, we know the quartz we consider to make a beam. Vibration is actually having a well-defined resonant frequency. F0 is equal to 1 over 2 pi square root of k over m mass. So that's the reason. So the way if we use it to make a vibration, this cycle, this period is well-defined. It's very repeatable with very small error. That's the reason we like to put the point. Yeah, but I'd like to answer. Yeah, but asking how is not our concern. We care. If we use it for clock, we want to repeat it. And so that after we keep vibrating for billions and billions of cycles, the error should be 0.00001 second. And we like this. Okay, good point. Good job. So that's the reason. Quartz. We use it to make a point. Now, but our computer is digital. Quartz is analog vibration. That means what? We need a converter. We need a circuitry to convert a mechanical oscillator vibration clock period into the electrical signal 0101. So this is a clock generator. It's going to do it for us. We need a very good clock generator and convert this quartz vibration into a digital clock 0101. Okay, so here, that's how we get it. Come from quartz because quartz is very reliable, right? But we want to convert it to digital. Now, this is the complicated clock generator, right? Even now, we are still working hard to improve the accuracy. There is in Silicon Valley, there's a silicon time, right? Silicon time. They use micro technology MEMS to make this clock. And this clock they use it for Wall Street, NASDAQ, right? Their transactions, they need a clock, okay? So in this way, the timing is very important, critical for them, right? To decide the price go up, go down. They use this their clock, right? The product from their company, right? So clock should be very accurate for microprocessor. Okay. Now this is an example. This is a clock generator. You see here, right? You see that? You take the oscillator pulse, mechanical, and they use a lot of gates and the module. Finally, you get the clock. Peripheral clock and the microprocessor clock is different. Generally, peripheral clock is the frequency is lower, slower, because why? Your I/O device works slower than the brain. Okay, so we have P clock and clock. P clock is longer. The clock period is longer than this one here clock, right? So this clock is generated for the 80, 88, 86 microprocessor. Example, connection, right? And this is the course, oscillator. And this is the system reset. This one is the clock generator for microprocessor. Very good. Okay. Now, clock waveforms. Clock is always 0, 1, 0, 1, 0, 1. Tick clock, right? Tick clock, tick clock. Okay? So that's the clock, right? 0, 1, 0, 1. Should be well defined, repeatable. And the older generation is megahertz. Now we're talking about gigahertz, nanosecond time period. Okay? And the P clock, oscillation signals. Clock to P clock. Typically, we have this relationship. What is it? The peripheral clock and the oscillation clock are provided to drive the peripheral ICs. The clock out of the P clock is half of the frequency of the clock. And the oscillator output is at a crystal frequency 3 times of the clock. It is okay? Any question? So oscillator clock is very accurate to the plastics. When you translate it into the microprocessor clock, slow down. You will go slide a little, okay? So this clock, we have a rule. T clock equal to what? 3 times of the T oscillator. And furthermore, P clock, the peripheral clock, the P clock, peripheral clock, is half of the T clock. So you say, oh no, this frequency is half, and the period is 2 times of the T clock. That's a relationship, typical relationship. Because every time when you do a conversion, you slow down a little. It is okay, right? So in this way, if we tell you what oscillation, what clock we need for your peripheral, then you can actually trace back to your T clock and oscillation clock. It is okay, right? So that's a typical relationship. 3 times the clock. Time is right? Double. Okay, double the oh no, here, right? Oh, sorry, this one T clock is this one. Sorry, this is 3. This is 2. This is 2. This is 3. Okay, right. So a oscillation clock is 3 times the clock. A oscillation also still the same. Oscillator frequency. Yeah, the original one is correct. That's the rule. Okay. Any question? Any question? Now let's design some clock. Also, we have a rule. What is it? Your frequency is 1 over T. Okay, right? So what does this mean? That means F clock is 1/3 of the F oscillator. F P clock is half of the frequency of the clock. Is this okay? We talk about frequency, reciprocal. Right? Now let's see how you design our clock. How you design the clock for our microprocessor. If I want, for example here, right? The clock of the microprocessor to be driven by 9 megahertz signal. What the speed of version of the microprocessor must be used and the frequency of the crystal microprocessor. What is it? If we want to run the 9 megahertz, what does it mean? That means the F clock should be 9 megahertz. Now, what should be the crystal frequency? We want this one to be 9 megahertz. Now, what's the frequency? Oscillator? How many megahertz? How many? What's the F oscillator? 3 or 27?
27?
21? 9 multiplied by 3. How many? How many? You want the clock to be. What's the oscillator frequency we need?
Is it 1 over T?
Huh?
1 over T?
We want the F clock to be 9 megahertz.
9.
And then what should be the oscillator frequency?
27.
Pardon me? Loudly?
1 over 9?
1 over 9. 1 over 9?
27 over 3.
27. Y over 3. Y over 3.
Does that give you 9?
Huh? Pardon me? How many? How many?
Does that give you 9?
Hmm?
27 divided by 3 is 9.
Why divided by 3?
You just said it.
Huh?
1,
See?
3.
So we wanted this one to be 9 megahertz. Then what is this one?
So that has to be, oh, that has to be 27.
F oscillator equal to what? Equal to 3 times of the F clock. Equal to 3 by 9 megahertz. That means you need to purchase a quartz with 27 megahertz oscillator. Is this okay? Right? Okay. So Christmas is coming. You are going to buy a lot of like a Christmas gift. Can you buy an oscillator for our microprocessor as a gift? What frequency? 3 times. Okay. It is okay? So the 27 megahertz. That's the correct frequency we should purchase for oscillator. And use this, we can change the clock for microprocessor at 9 megahertz. Okay, any question? All good? So we need to design this, right? Design the clock. Design the clock. Yeah, we will continue till 3:30 and then we finish early, right? And then maybe after we finish this, and then we can invite you to talk, right, about your project. Okay, now let's look at the bus cycle. Do you dance? Do you dance? Christmas is coming, right? Dancing party, dancing party. Okay. Anybody good at dancing? Everybody like it. So when we dance, we follow a pace. 1, 2, 3, 4. 1, 2, 3, 4. Right? That's the dancing. Now, similarly, we say that what? When we do this microprocessor execute a instruction, for example, move AX SI. What are we doing here? What are we doing here?
Moving SI.
We are moving what? Byte word data. How do we know?
Data.
Word data, right? From where?
SI.
From memory to where? to register. Now, what value should we set to control this process to happen? We need a memory reader or memory write. Data transmitter, receiver, bar, which one, 1 or 0? If we do this, actually a lot of signals should be set and reset in order to get the job done. What are they? Remember that what? Our memory control interface. Right? And then a data transmitter receiver bar equal to 1. Can you tell us the value based on the instruction we are doing? And why you set those values? Can you tell us? We just yeah, very good. So we just write remember those names, right? Memory interface, we then know that there are a lot of control signals. Now we give you a real example. We are doing this instruction. This instruction, what are we doing? We know if we are doing the memory operation in memory mode. And plus, are we read or are we write? Are we read or are we write? Read, very good. And then are we sending out the data or are we receiving data from microprocessor view?
Sending.
Receiving, right? Receiving, very good. Now, how should we set those values to make this happen? Yeah, can you help us, right? And each of you, can you write your answer? Because how the microprocessor get the job done, it is just setting those control signal interface, memory interface signals in order to get the job done. And the microprocessor cannot use a hand to make this happen. Microprocessor can only set those values, control values, to get the job done, based on what instruction you are executing. Yeah? Yeah. Or maybe you control the like work together. If we, yeah, okay, like so yeah, even like we encourage you to discuss with each other, to help each other, right? Right? And then can you also set this value? What are we doing? How can we make this happen? That's the reason we ask you to remember those math and remember those things. Because we can use them in the discussion. According to the name, you have a bar, you don't have a bar. Should we set it to be 1 or should we set it to be 0? Right? Everything inside the microprocessor should be well defined. No confusion, no misunderstanding. Otherwise, it's a nightmare. So we know that our computer is very trustworthy. You trust your banking account information on your computer, right? If you make any mistake, your money is gone. But that should be very trustworthy. How to make it trustworthy? You have to well define all these procedures, right? The process, right? Make sure no mistake. We are reading a memory, right? Reading memory. So memory read bar should be enabled. Read bar 1 or 0. Should be a 0. And we are not writing. We should disable it. Then we set it to 1. Yeah, we're not writing, so we should set it to 1. Right? Disable it. Disable it. Yeah, 1. Yeah, 0, 1. And we are in the memory mode. Enable memory mode 0. And we are receiving data. So transmit receive bar. Congratulations. You did it, right? You did it. What's your name, please? Dija, right? Thank you so much. I'm so proud of Dija, right? Dija. Okay, you get the job done. You make sure they follow our instruction to get the job done. Right? How? Set those values. Set those values high or low. Okay, so it is okay. So I think the data get a great job, right? So how? First, understand what we are doing. This instruction we are reading data from memory into microprocessor. if we understand this, then we can set those values. This is a memory read operation. Memory read operation. To read the memory read about should be enable 0. And then we are not writing, disable it 1. And then we are in the memory mode, set this memory bar, set it 0. And then we are what? Receiving data. Receiving bar. Good job. Congratulations. Right? Any question? See? Well defined. That's the reason we want you to remember the names. Because if we don't remember the names, we get lost. Should we set them to be 1 or 0? We don't know. Okay? Now, let me see another one. This one, what should be the value? What should be the value? Are we reading or are we writing?
Reading.
Huh? Reading or writing?
Writing.
Writing, very good. And then what should be value? What should be the value? Oh, you, huh? Want to give it a try? Okay, good. I think you can together, right? I encourage you to discuss with each other. Yeah, you want to invite some friends to together? Yeah.
You want to come?
Oh yeah. Okay. And everybody, can you also mark your values? Okay. So what are we doing here? This one is for this one for this. But if we change to this instruction, what should be this one? You can use the red color mark for the bottom. Are we reading or are we writing? Are we sending out or are we receiving back? Are we? What are we doing? Are we sending out or are we writing? Yeah. We are not reading. We are writing. We are in memory mode 0. We are receiving. We are writing out. Right? Now you know how to control. Good job. Right. Good job. First question, what are we doing? Second question, what should we set those values? Make it happen. Yes. Okay, you're done, right? Okay, very good. We are not reading, we are writing, we are in the memory mode, we are sending out there. Congratulations, right? Good job. I'm so happy. Okay. Both of you, right? Good job. Okay. I'm so happy for you. Now you get the point. How to control this memory IO interface? Simple value. And what value should we set?
Yes.
Those control inputs. That is what we ask you to remember. Because in this discussion, yes, which one? IO bar. Oh yes, you're right. Okay, we're still in memory mode. You're right. Okay, so this one should be 0. So this red value is 1. Okay. So this one should be 0. Still memory mode. Still memory. But if it's IO, then we should be 1. Any question? Now you can design your microprocessor, right? Just by controlling those interface values. And those interface are the key to make things happen. Okay? Now, let me show you another one. We're dancing. If we want to read or write the data, how can we get it just by one step, or should we do it in multiple steps? One step or multiple steps? One step or multiple steps? If we want to get a job done, how many stages do we have to do it in one stage? Say, oh, Professor, I want a Christmas gift. Okay, and I click a magic button, your Christmas gift immediately show up. Is that right? No, it will never happen. You need to first place the online order, and they are going to find it from warehouse. And then from the warehouse, they can send it to USPS. And the USPS going to send the package to your address. And then finally, they are delivered to you. See, right? So you see that you have multiple states. And then similarly, if you want to read the data from memory, it's not a magic button. It's multiple states. First, broadcast address. Tell memory where's the data. And the memory is going to locate that piece of data and then bring it to the data bus. And then from the data bus, it's going to send it to your microprocessor destination register. At least 1, 2, 3, 4. Is it okay? So that's the reason we said what? A bus cycle is different from a clock cycle. Clock cycle is the clock frequency, 1 over clock frequency, 0, 1, that's 1 clock cycle. But typically, in order to accomplish a task, the time it needed, we call this a bus cycle. A bus cycle to get a job done, typically we need 4 clock cycles. Right? That's a typical one. But sometimes longer, sometimes shorter. Typically 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. It is okay? Right? Just like your unknown order, my order. Place out the order, get it from the warehouse, send the USPS, deliver the package. 1, 2, 3, 4. 4 clock cycles. Okay? So in this way we tell the difference. Bus cycle is different from the clock cycle. Bus cycle to get the job done. Okay? So anyway, typically it's like this one in here. Now if sometimes you want extra clock cycle, what should we do? Here, for example, professor, can you give me more time for homework 1, project 2? That's for extension time. Okay, we need more time. Similarly, this is typically 4 clock cycle. What do you think say? How can we say introduce actual way state TW? N TW. How many extra clock cycles you want? Just request. Okay, and then microprocessor will insert those way state. Okay, so in this way, typically 4. But it could be more, could be more. So this one is actually showing us, right? Bus cycle, clock cycle. This is get job done. This is clock cycle, 0, 1, 0, 1, 0, 1. Actually see the memory control signal. It's 1, 2, 3, 4. 1, 2, 3, 4. That's a bus cycle. 4 clock cycle, right? And then sometimes we can introduce extra. For example, this is 1, 2, 3, 4. But you need an extra. You need an extra and you insert extra weight cycle. Okay, horizontal cycle, right? You can extend it. Now, actual bus cycle. Actual bus cycle, how long it is? The actual bus cycle is n plus 4, 1 clock cycle. N is the weight state, extra state you request. If you don't request it, it's just 40. Otherwise, n plus 4. Is this okay? 4 clock cycle is a typical bus cycle. But sometimes we can introduce extra. For example, if we tell you the frequency clock cycle is 8 megahertz, then you can calculate the T clock cycle, 1 over F is 125 nanoseconds. Now, if you say that what, you achieve your bus cycle to 40, 500 nanoseconds. However, if you have 2 additional weight states requested, then total length of this bus cycle, m plus 4 T, which is 700 T, giving more time to finish this instruction. Any question? That's the actual time. Now, with this information in mind, we are ready to introduce to you one mechanism for a what? A read bus cycle, 8088 microprocessor. how many bus cycles do we need, and how can we get a job done? How can we get a job done? Now, let's take this example. First, let's look at what? 8088 microprocessor. Right? 8088, the memory, just one byte. From 0000H to FFFFH. Right? The array, the address, right, the data. Now we have data bus, 5 directions, 8 bit, here's 8088. The address bus, 20 bit, 890 to 80. If we have a 8086 microprocessor, it's different architecture. Lower back, higher back, even back, all the back. We have two backs. So lower back, higher back, even back, all the back with the address. The address bus A90 to A1 broadcast the both. And the data bus D set higher byte, higher 8 bit for higher back. Lower byte, lower 8 bit for the back. Data bus. Address bit A0 is used as an enable, chip enable for lower back. Higher back enable is enabled by PHE bar. Both of them are too low. It is okay? Now, if I have my data is in the lower bank, that means it has an even address. If an even address A0 bit, address A0 bit is 1 or 0. 1 or 0. 1 or 0. Huh? 1 or 0. If you say move AX 1, 2, 3, 8H. Now, lower bank or high bank, where is it located? How do we know? How do we know? Memory. AX 1, 2, 3, 8H. Lower bank with this data memory. Which bank? Which bank? Lower bank or high bank? Even or odd? Odd again. Even or odd?
It's even.
Huh?
Even.
Even, right? How about A0? Bit A0 is 1 or 0? 0. Very good. Very good. And 0, enable, disable. I to low, enable. Then enable back. It is okay? So the way A0 is 0, enable. Lower back. And at this moment, we should set BHE bar to be 1. However, given the word, if the word is aligned, then we can also set this one to be 0. So we can grab the whole word one time. Is it okay? Right? But if it's a byte, say AH, then you should set BHE bar to be 1. Because your data doesn't come from the highlight. Disable. It is okay? However, if my address is odd, 1, 2, 3, 9H, now tell me A0 is 0 or 1? 9. Even or odd? Odd. A0 is 0 or 1? 0 or 1?
0. Oh, odd or 1?
1, right? 9 is 1001. 1, enable, disable.
Disable.
Disable. Disable. Because your data is actually here. It is in this bank. In this case, we should have said this one. Is this okay? Any questions? So it's a case by case study. Where's your data located? The byte or word? If the byte, right? And the lower bank or high bank. And then which bank should we enable? So we always use the A0 bit to enable the lower bank. And use PHE bar to control the high bank. Any question? So far, so good? Right, so we have control, Now we're going to show you here, two banks. 8088 memory has one bank, 8086 memory has two banks, even bank and lower bank. Now the data transfer, if we have instruction memory operation, the data transfer actually depends on whether you're talking about 8088 or 8086, whether the data is byte or word, and even whether it's even or order address, a line is a line. That makes a difference. We're going to show you one example, 8088, and we are going to ask you to digest it. Next time, we're going to ask you to analyze the 8086. Okay. How did that? We first from 8088. 8088 data byte transfer. For example, we are talking about this one, 8088 byte. For example, go AH 1, 2, 3, 4. 8088 make it easy. Bank memory only one bank. Okay. Alright, and then we are going to read the data from this location to here. First, the microprocessor is going to calculate DS1, 2, 3, 4H. That's the physical address. Equal to A19 to A0. Physical address. And this physical address is going to be broadcasted along the address bus. It is okay? Right? Along the address bus. And then we're going to locate this data, send it out to the data bus. From the data bus, go to destination page, right? That's what's happening. And the whole process can happen for multiple clock cycles, but only for one bus cycle. Okay, easy. It's okay? One bus cycle for memory read write in byte data of 8088 microprocessor. One bus cycle. However, if this is 8088 for word data, how many bus cycles do we need? Word data. Word data. And we just change this one to AX, word data. How many bus cycles do we need? How many bus cycles do we need? We need 2 bus cycles. Because while your data bus is only 8 bit, so each time you can only handle 1 byte. Your word data is 2 bytes, so you have to do it one by one. It is okay? It is okay? 2 bytes okay. Word. Only one hand. How many times can I get both? First I reach out for this one. Send to me. And then I increment the address for the next byte. And again, reach out, get to H. How many bus cycles? 2 bus cycles. Alright, so what's the procedure? You first calculate the physical address, broadcast along the address bus, locate the lower byte of the data, send it to the data bus, go to the microprocessor AL register. After that, increment your address by 1. What is the next byte? Locate the data, broadcast along the address bus. Locate the data, take it out to the data bus, send it to the microprocessor AH register. 2 bus cycles are needed. Any question? Okay, right? Okay, that's for 8088, right? How about 8086? 8086, if it's a byte data, how many clock cycles, bus cycles do we need? How many?
One.
Pardon me? How many? How many?
One.
One. Very good. Because you only have one byte. Okay. So say for example, $80.86. Move A H 1, 2, 3, 4 H. One bus cycle. Regards even against order, then we don't care. Right? However, if there is even address, even lower back. A0 is a 0. Bank high enable bar should be set to 1 because your data is in the lower back. A0 low, you can enable it. So we first calculate the physical address DS1234H physical address. Broadcast to A19 to A0. A19 to A1 enable both. But this one broadcast both. And then A0 enable this one. Locate the data here. Send it to the lower byte of the data bus. Because now your data bus has 16 bits. So we're going to send it to the lower byte. D0 to D0. Right? And then from this data bus lower byte, go to the AH register. One bus cycle. However, if this one is in higher rank, for example, if this one is a higher rank, what happened? How many bus cycle? How many? Still one bus cycle. Because why? You still have byte data, only one byte. But then now your A0 order. A0 what you want. Then you should set bank high enable bar to 0 to enable this high byte. Disable A01, disable to that. You broadcast A19 to A1 to both, but only this one is enabled. Locate this data, send out to the data bus, higher byte of the data bus. E15 to E8. From the data bus, go to H register. One bus cycle. Any question? However, if I'm talking about word data, what happens? First, talk about aligned data. What are we doing? Word data. Aligned or misaligned? Even is divided by 0. Aligned. If it's aligned, that's an easy case. Lower byte, higher byte. Lower byte, higher byte. It is okay? Aligned. What does this mean? I have two hands. Two hands. Lower bank and higher bank, I can hit them both. Go to the X register. How many bus cycle? How many? How many? Only one bus cycle. Because they are aligned, right? Aligned. Our data bus is also simplified. So what happened is calculate the physical address. It's one bus cycle. Physical address is 1, 2, 3, 4, H, DS, go to A19. This one will be fine, right? Now what happens is what? This is an even address. A0 to 0, enable. We also set a BHE to be 0. So we're going to set A0 equal to even. simultaneously enable lower byte and higher byte. Get both higher byte and lower byte. Send them to the data bus, higher byte and lower byte. D0 to D7, D8 to D15. And then from data bus, go to X-ray. One bus cycle. Any question? Now, we change this one to 5. How many bus cycles? Word data misaligned. What does this mean? Misaligned. This handle is this data. This handle is this data. Can I get both? Can I get both? No. Because they're swap. Right? So that's the reason we have to do 2 steps, 2 bus cycles. First one, go to lower, get it, send the high byte the bus. Then increment address, go to next byte, get it into the data bus. 2 bus cycles, give it to 0. Okay, how? We're going to do 2 steps. First step, we're talking about 5. Order address. Order address A0 is 1. Disable lower byte. And then BHE we set to be 0. And then enable the high byte. And you're going to grab, you broadcast the address, grab this high byte. Send it to, this is actually lower byte of your data. But you're going to send it to the high byte of your data bus. But the microprocessor knows this is for lower byte. It's going to send it to AA address. And after that, increment your address by 1. So that this will become 1, 2, 3, 6 edge. Increment by 1, then become even address. Even address A0 is 0. Enable the back. Then we should set the BHE bus to 1, disable high back. And then we send further address to each other with higher byte with data actually stay in the lower byte of your memory. So to take it out, the lower byte of the data bus. But the microprocessor knows that this is for high byte data, send it to AH. Done. Very complicated, right? But